Many substances can exist as a gas, a liquid, or a solid, but even though matter can exist in different states, it maintains its same chemical composition. As chemists studied these different states of matter, they came to understand that there was a regularity and pattern about the way that all substances behaved. We are going to look at some of these patterns and the theories that have been developed to explain them. There are gases all around us. The air we breathe is a mixture of gases that are colorless and odorless. Except in windstorms, we are rarely aware of the air, but we would not survive long without it. There are many different gases, but despite their differences in chemical composition, they all have similar characteristics. Gases fill containers completely. The gas inside this balloon is evenly distributed, just as the air in a room is distributed into every corner. Gases have mass. A balloon filled with helium is lighter than one filled with air, but both gases have mass. Gases can be compressed. The tires of cars hold compressed air. When the pressure rises inside the tire, the air molecules are pushed closer together. Scuba tanks used by divers have compressed air. And propane tanks used in barbecues contain compressed propane gas. Gases exert pressure. This inflated sports dome holds its rigid shape because the air inside the structure has greater pressure than the air outside. Gases mix rapidly. When two or more gases are mixed together, they rapidly spread out and the particles mix together. This is called diffusion. The pressure of a gas depends on its temperature. The higher the temperature of a gas, the higher its pressure. The lower the temperature, the lower the pressure. These characteristics have been found to be true of all gases, and scientists developed an explanation for this behavior called the kinetic molecular theory. The kinetic molecular theory explains the behavior of gases by looking at the forces of the particles in the gas and the energy they possess. A gas contains very small particles. They are either molecules or atoms. The distances separating the gas particles are relatively large. The space between the particles allows them to be pushed together. The gas particles are in constant, rapid, random movement. This is one of the reasons why gases immediately fill their containers and why they quickly mix or diffuse together. Because gas particles are in constant motion, they collide with each other and with the sides of the container, but they do not slow down or lose energy. This is called elastic motion. The kinetic energy, the energy of movement, depends on the temperature of the gas. Temperature is actually a measure of how rapidly particles are moving or vibrating in the material. At higher temperatures, the particles have greater kinetic energy and move more rapidly. At lower temperatures, they have less kinetic energy and move at a slower rate. Finally, gas particles exert very little force on each other. They are like independent agents, bouncing about, uninfluenced by any other particle. Some of the earliest achievements in the science of chemistry in the 17th and 18th centuries resulted from the study of gases. There are only 4 factors or variables that influence the behavior of gases. They are the pressure, volume, temperature, and amount of the gas. Barometers measure atmospheric pressure, or the force of the air on the surface of the Earth. This apparatus is a type of barometer. At the beginning of the experiment, liquid mercury sits in a reservoir at the bottom, and there is a vacuum in all the tubes. Atmospheric air is then allowed to enter the apparatus. Its pressure on the mercury in the reservoir pushes the mercury up the tube. The greater the pressure, the higher the mercury will climb in the column. Barometric pressure, when combined with knowledge about air currents and other factors, can give an indication of the weather. High pressure generally indicates settled, fair weather, while low pressure indicates unsettled weather. Robert Boyle, an English chemist, studied the relationship between pressure and volume of gas. This apparatus demonstrates his findings. Liquid is in the syringe and tube, and air is trapped in the rest of the sealed tube. When pressure is applied by the syringe, the volume of air decreases by a proportional amount. This is a demonstration of Boyle's law. It states if the temperature and amount of a gas remains constant, the volume varies inversely as the pressure changes. Jacques Charles, a French scientist, studied the relationship between temperature and volume of gas and found that there was a direct and consistent relationship. If gases are heated, they expand. When cooled, they contract. The air in this balloon is being cooled by liquid nitrogen, which makes it contract. It expands again in room temperature. This is a demonstration of Charles's law, which states the volume of a gas is directly proportional to its temperature. It is Charles's law that explains how hot air balloons can rise off the ground. The heater at the bottom of the balloon heats the air inside the balloon and it expands in volume. As a result, it becomes lighter than the air that surrounds it. That causes the balloon to lift off the ground. Amedeo Avogadro, an Italian scientist, studied the relationship between the volume of gas and the number of gas particles. He found that all gases show the same physical behavior. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain an equal number of particles. John Dalton, an early English chemist, studied a mixture of gases and found that equal volumes of different gases exert the same pressure. His other finding came to be known as Dalton's law. It states that the sum of the pressures of all the components in a gas mixture is equal to the total pressure of the gas mixture. All of these laws deal only with the four variables: pressure, volume, temperature, and amount of the gas. Chemists have been able to combine these laws into a formula called the ideal gas law, which is a powerful tool that can predict the behavior of gases under various conditions. The kinetic molecular theory was first developed to understand gases, but it can be used to describe the characteristics of all states of matter: gases, liquids, and solids. In fact, its true name is the kinetic molecular theory of matter. This theory explains the behavior of all matter by examining the intermolecular forces between the particles and the energy they possess. It has three basic assumptions. First, all matter is composed of small particles, either atoms or molecules. The distance between the particles determines the state of the substance. Second, the particles are in constant motion. And thirdly, this motion is different for the three states of matter. All substances at a given temperature have the same amount of energy. That energy comes from the temperature or heat. At room temperature, some substances are a solid, others are a liquid, and still others are a gas. The reason for these differences is the strength of the intermolecular attraction between the particles. When a substance is a gas, these forces are weak, and the particles are far apart from each other and in constant disorder. they move freely about in a straight line motion. When they collide, they do not lose their energy. When a substance is a liquid, the forces are stronger, and the particles are in a state of partial disorder. The intermolecular forces hold them much closer together than when the substance is in a gaseous state. Liquids have much higher densities than gases and are not very compressible. When a substance is a solid, there is a strong intermolecular attraction between the particles. That attraction holds them close together in an ordered relationship. Solids have high densities and are virtually incompressible. They appear to be in a fixed position, but in fact the particles still possess kinetic energy and are always vibrating. What determines the intermolecular attraction of substances are the chemical bonds between the molecules and atoms. Ionic bonds and metallic bonds are almost always solids at room temperature because there is a strong electrical force between the ions, holding them together. Covalent bonds, like organic molecules or water, can be solids, liquids, or gases. They span a wide range of strengths, but are always weaker than either ionic or metallic bonds. Temperature is the primary variable that determines whether a substance is a gas, a liquid, or a solid. It takes kinetic energy, or heat, to convert a substance from a solid to a liquid and then to a gas. The kinetic energy of the heat makes it easier to break the attractions between the particles of molecules and atoms. Conversely, when a substance goes from a gas to a liquid to a solid, it loses heat. All elements, and most substances, have temperature points where they convert from a solid to a liquid and then a gas. Even metals with very strong bonds can be converted to liquid and vapor if enough heat is added to the substance. The old saying, "as slow as molasses in January," describes viscosity, an important property of liquids. Under room temperature conditions, molasses is a thick, viscous liquid that pours slowly. It is a sugar, and there are strong attractions between the molecules. When the temperature decreases, that attraction between the molecules becomes even stronger because there is not enough kinetic energy to let the particles fall apart, and the molasses flows more slowly. This is the reason why "as slow as molasses in January" accurately reflects the behavior of molasses. Surface tension is another property of liquids. Water bugs use surface tension to run along the top of water. Dewdrops hold together because of the same phenomenon. The reason for surface tension is that the molecules at the surface of the liquid have attractive forces downwards and sideways, but not upward. That imbalance of forces results in a stronger attraction to neighboring particles at the surface and results in the surface tension. Liquids with differing chemical compositions have different levels of viscosity and surface tension. Water, however, has some unusual properties. A water molecule is H2O, two hydrogen atoms linked with one oxygen atom. There is a strong bond within the molecule, but there is also a strong attraction between molecules of water, because the hydrogen atoms of one molecule are attracted to the oxygen atom of another molecule. This intermolecular force gives water its unique characteristics. Because of the strength of this intermolecular force, it takes quite a lot of heat to pull the molecules of water apart and become a gas. As a result, water has a high boiling or evaporation point relative to other liquids, and it can absorb or release large quantities of heat. This has very important consequences for weather patterns on the globe. Land that is close to large bodies of water usually has moderate temperatures. and there is frequently heavy rainfall in mountains because as the air rises, the temperature drops, and it cannot hold as much water. Perhaps the most unusual property of water is that its density when it is a solid, ice, is less than its density when it is a liquid. Almost no other substance has this characteristic. The reason for this is that the hydrogen bonds of the water molecule keep other molecules from getting close. When water is in the form of ice, it results in fewer molecules in a given volume, and thus gives the ice a lower density and allows it to float on top of the water. Particles in solids such as metals, plastic, or wood are made up of atoms, molecules, or ions, which remain in fixed positions. The density of substances when they are solids is almost always greater than when it is a liquid. The most common exception of that, we know, is water. Many solids are crystalline in structure. The crystals have definite arrangements of molecules because of the intermolecular forces, or attractions, that repeat themselves throughout the structure of the solid. These drawings show some of the most common crystalline arrangements found in solids, but there are many others. The physical properties of each solid, such as hardness, brittleness, melting point, and electrical conductivity, depend on the molecular structure and the strength of the attractive forces between them. Some substances look like solids, but their structures are more characteristic of liquids. Plastic, rubber, and glass are called amorphous solids. In composition, they have the inherent disorder of liquids that have cooled to the point where they have become solid, but they lack a crystalline structure. When cooled even further, they lose their flexibility and become brittle. The understanding of the characteristics of gases, liquids, and solids has had an impact on many aspects of our lives. It has been vital in the development of many of the technologies in our modern world. When matter changes from one state to another, it changes its chemical composition. True or false? Gases fill containers completely. True or false? The pressure of a gas depends on its temperature. True or false? The kinetic energy of gas depends primarily on pressure. True or false? Boyle's law states if the temperature and amount of a gas remains constant, the volume varies inversely as the pressure changes. True or false? The kinetic molecular theory of matter only explains the behavior of matter when it is in a solid state. True or false? It is temperature that is the primary variable that determines whether a substance is a gas, a liquid, or a solid. True or false? Heat makes it more difficult to break the attractions between the particles of molecules and atoms. True or false? Water is a unique substance because when it is a solid, its density is less than when it is a liquid. True or false? All solids have a crystalline structure. True